time to learn about ultraviolet light. It might save your life. That's because ultraviolet light is more energetic than regular light. We sometimes call it ionizing radiation because it has the power to ionize the electrons in molecules, like DNA, and cause damage. UV light is invisible to us, but its energy can make other objects glow, like this pair of socks. They absorb the UV light and release that energy as visible light. It's actually the detergent residue that glows and makes them look really clean, whiter than white. It doesn't always take UV to make things glow. I can get these fluorescent liquids to glow just by using a blue light. But I can't get the green or yellow by using the red light. There's something that blue and violet lights have that the other colors don't. They are more energetic, higher in frequency. Their high-frequency light is absorbed and re-emitted as lower energy light. These plastic beads are sensitive to ultraviolet light. Even in sunlight, they will change color. But I get a different effect when the sunlight passes through a pane of window glass. That gives us a clue that there are multiple colors of ultraviolet light. Unlike visible light, ultraviolet light is sometimes blocked by glass. These fluorescent rocks glow in multiple colors when exposed to UV, but this clear glass pane prevents much of this. Some of the UV still gets through though, but not all. The three colors of UV are named near, mid, and far, or UVA, UVB, and UVC. The sun emits all three. UVC is the most energetic, and it's easily blocked by the atmosphere and glass. It is sometimes produced artificially by people to kill bacteria on tabletops, keyboards, meat, and treated sewage. UVB is partially absorbed by our atmosphere, especially the ozone layer, and it causes sunburns. UVB is blocked by glass, so you're less likely to get a sunburn through glass. This is quartz. It's made of the same material as glass, but it's extra pure and cooled slowly. And unlike regular glass, quartz is transparent to UV light. I have here some man-made quartz glass on this UVC lamp. Like I said, it has to be very pure. It's the impurities in glass that do most of the absorbing. Here's a piece of willemite illuminated with UVB. A common glass microscope slide blocks the UV light, but a quartz glass slide has no effect. Quartz glass is transparent to ultraviolet light. Then there is UVA. This is the ultraviolet and black light, and this is the type that is not blocked by glass. Unlike UVB, UVA penetrates deep into the skin and causes damage beneath the surface. Along with UVB, UVA is the type that causes the most skin cancer. Therefore, we cannot rely on glass alone to protect us from UV light. We need sunblock. Most good sunblocks and sunglasses will advertise that they block UVA and UVB, broad spectrum. They don't even bother to mention UVC because there is so little of it that reaches Earth's surface. Electrified mercury vapor gives off a lot of ultraviolet light, and for that reason, we often use it in fluorescent lamps. The UV light is absorbed by the fluorescent paint on the inside of the glass. That paint glows in a convincing white. But isn't spending that much time under ultraviolet light dangerous? Well, once again, the glass protects us from the more energetic UV. This is the mercury spectrum. I'm projecting it onto a piece of styrofoam. The ultraviolet light is normally invisible, but this piece of paper fluoresces to show where the ultraviolet lines are. This is the experiment that first convinced me that ultraviolet light was real. Inspired by William Herschel's discovery of infrared light in 1800, Johann Ritter performed this new experiment in 1801. Ritter again split the sunlight with a prism into the normal rainbow. He arranged for the light to land on silver chloride salt, which turns brown when exposed to light. 20 years later, this chemical would be used to make the first photographs. Anyways, as expected, there was an invisible light beyond the violet side of the spectrum. It's a well-known fact that insects can see ultraviolet light, and most people think this is so they can see flowers better. But that's incorrect. The insect predates the flower by hundreds of millions of years. It's the flower that is adapted to the eyes of the insect. Insect eyes see UV because the shorter wavelengths offer advantages to the eyes of small creatures. First of all, when your eye is smaller, you want it to be sensitive to more energetic light, because then you will need less of it to see. And secondly, the shorter wavelengths reduce the diffraction effects, which allows for insects to have smaller eyes, and hence more compound eyes, and thus better insect vision. Many flowers have distinctive markings that are only visible in the ultraviolet, like little bull's eyes evolved to attract the pollinators. Hi, I'm painting a flower, but I took special care to mix fluorescent dye that I got from a highlighter into it. This will make it look more interesting under UV light, more like how bees see it. This is an activity you might want to do with your students. It's easy to extract the highlighter fluid if you use rubbing alcohol. As an alternative, you can also use laundry detergent. Check it out. This scorpion fluoresces in UV light. Fluorescence is common among organic molecules. In this case, it's the amino acid tryptophan. Most fluorescent organics contain similar structures of multiple carbon rings. For example, the quinine found in this tonic water, or the chlorophyll in this extra virgin olive oil, or the fluorescein in these highlighters, or the luminol in these glow sticks. Red, green, blue. This sheet contains a phosphor, that is, a dye that is phosphorescent, meaning it glows for more than a microsecond. But it doesn't mean that it contains phosphorus. In phosphorescence, the atomic transitions that release the energy are inhibited for quantum mechanical reasons, so the energy is released more slowly. In the case of fluorescence, the energy is released immediately, but it takes longer for phosphorescence. Phosphor is a general term even for cases when phosphates are not involved. These glowing objects are pretty common, like the oscilloscope screen or a CRT TV screen, and most toys that glow in the dark.